Hello, in this video we are going to derive the mass conservation law for fluid dynamics. So to start deriving the mass conservation law, we need to first define an element of fluid. So let's just consider this volume of fluid, which I will call V. So this is a volume that has surface S, and I'm going to here describe an element of surface, which I will call ds. And that element of surface has a normal, which is n, and I will call this the outward pointing normal. So it points outwards from the fluid. This is a convention. There are other fields of physics in which the normal is taken to be pointing inwards. I believe that electromagnetism is one of these areas. And for instance, we can look at the velocity at the surface, for instance, of this fluid, of this volume of fluid, and say that at this point it goes in this direction. Okay, so this is essentially our volume of fluid, and we're going to work from this. So for instance, well, we're interested in mass conservation. We can look at the total mass in this volume of fluid V, and that total mass, we will call this capital MV. That total mass is nothing else than the integral over this volume of the density rho integrated over the volume. So this is the mass density, and it's expressed in kilogram per square meter, per cubic meters. So this is in kilogram per cubic meters, okay? Or the unit in terms of dimensions would be mass times L to the minus 3. Okay, so here we're interested in understanding how this mass changes within this volume of fluid to establish mass conservation. And so the mass of fluids within V can only change if mass is carried in or out of V. In other words, what I'm saying is that my rate of change of mass within my volume of fluid, okay, is going to be equal to the amount of mass that is carried in or out of V. That is to say, the amount of mass that is crossing my boundary, my surface S. So that will be the integral over S. We're looking at some mass, so it's going to be a density, and that density is carried by the fluid velocity, so there will be U. It's carried across that surface, whose element of surface is ds, and it's oriented with the outward pointing normal. So we're looking at U dot n, that is to say how much of that velocity goes across perpendicularly from that element of fluid, and that is transporting the mass, right? It's transporting this fluid density. So we're looking at this, but of course, because n is outward pointing, when U is aligned with n, then what that means is that this is going to be positive. What is happening here is that we're taking mass out of this volume of fluid. So because n is defined as the outward pointing normal, we need to add a minus sign here. As I said, I shall say again that if U and n are aligned and point in the same direction, this is positive, and so the rate of change here should be negative in case this is positive, because we're taking some mass out of our fluid volume V. So I put this minus sign here. So now we can look at this expression. Well, this is essentially telling us that the rate of change of mass in our volume V is equal to is equal to this, how much mass is carried in or out of the volume V. So that should be an exact, that is an exact law. If we're not convinced about it, we can look at its dimensions. This term is a mass per unit time, okay? And when we look at this term here, that's the density. As I said earlier, it's m times L to the minus 3. This is a velocity, so because it's a velocity, it's L times t minus 1. N is a unit vector, so it doesn't have any dimension. And ds is an element of surface. That is to say, it's going to be L2. Okay. So now if I multiply these three dimensions, what I get is m. This is the only times that m is here. L to the minus 3 times L squared, so that's 1. And I have t to the minus 1, okay? So this is a homogeneous expression in terms of dimension, which comforts us that this is a correct expression. Okay, so now I continue by essentially including, by replacing mv by its definition here. So that gives us that d by dt of the integral over the volume v of rho, oh sorry, this would have been dv here, absolutely, of rho dv is equal to minus the integral over the surface of rho u dot n ds. Okay, so that is our first step, replacing here. But we notice here that I have not said anything about v. I'm just going to define now that v, for the sake of this demonstration, that v is a fixed volume. So if v is a fixed volume, that this differentiation here can get into the integral sign. So v is fixed, gives us that that's the integral over the volume of d rho over dt dv, okay, and it's equal to the same right hand side, integral over s of rho u dot n ds. But what is nice here is that we observe that this is an integral dot n ds, and so we can apply the divergence theorem. To get the following expression. So this is giving us that this is the integral over v of d rho over dt dv, and it's equal to the integral, to minus the integral over the volume of the divergence of rho u dv. Okay? So this is the first step of this demonstration, and of course from this we can rewrite this expression by sending everything onto the left hand side and within the integral. So we can say that this is the integral over v of d rho over dt plus the divergence of rho u, and this is to be integrated over the volume, and we can say that this is 0. Okay, so that gives us this expression. This nice expression. But remember that our volume of fluid V, we've not said anything else but that it's fixed. We haven't said anything about its size. So that expression here, as a consequence, has to be valid for any volume V that is fixed. So that volume can be large, but it can also be very small, down to the blob of fluid, you know, down to the size of a fluid particle with quotation marks. So because V is arbitrary, we can write that this expression is valid pointwise. And therefore what we can write is we can just discard this integral altogether and say that d rho over dt plus the divergence of rho u equals 0. In other words, saying that I'm integrating over such a small fluid element, such a small fluid volume, that I can consider it as a point. So we can express this divergence in a bit more in an expanded fashion. So we can also write that this is d rho over dt plus rho divergence of u plus u dot grad rho equals 0, and we can group this partial derivative and this u dot grad operator into a total derivative for rho, or Lagrangian derivative for rho. So that would be d rho over dt plus rho times the divergence of u equals 0. And whichever of these formulations you pick your favorite, whichever of these, these expressions are commonly called the continuity equation. So these are important state equations for in fluid dynamics. The last remark I'd like to make here is in the case we have a fluid whose density is constant in time. That's the case of the incompressibility. So if the fluid density is constant over time, the continuity equation becomes, and it just becomes, so this first part of the equation essentially is 0. Because we don't have a fluid of density 0, then what's left of this equation is the divergence of u equals 0. This is called the incompressibility condition or constraint. And the fluid is said to be incompressible. In this video, we've seen how to derive the mass conservation law for fluid dynamics, and we've also seen how it changes in the case that the fluid has a constant density. In other words, in the case the fluid is incompressible. This concludes this video on mass conservation.